Our tutorial will be a little bit long. On the other hand, I have lots of tomatoes. Completely unrelated announcements, but they will both show up to the tutorial. Okay. So today we're going to learn about the structure of a group. So first, we're going to learn about the representation of the group. Well, the idea is some groups are very abstract, and we're all very good at matrix multiplication. So let's make all the group elements into matrices. Okay, then we'll study in detail about the structure constants. And this is very, very important for our group. Hopefully we will see. And then the last, we shall study, revisit our very, very important group, Poincare group. And actually, we're going to spend the entire tutorial on Poincare group and answer the following very, very physical question. What do we mean when we say a particle has mass? And if you do the optional problem, you will also answer the question, what do we mean by a massive particle has spin? So this group is very instructional. So that's what we'll do. And as a start, guess we should recall what is a group. Well, remember a group is a set J that with some multiplication defined, which this multiplication is just a binary operator, that we have some axioms, says that J is closed. And then we have association too. And then we find our identity. And then we have our inverse. Okay, so that's what we learned yesterday. Such an object is what we call a group. And then we shall try to study the representation of the group because we just love matrices. Oh, they're just very useful. What we say is that given a group element, which could be some rotations between a point of a triangle to the other triangle, can be very abstract. But we decided to map them onto a matrix anyway, and we call this matrix D as a function of G. And let's say this is a M by M matrix. Okay, so for every single group element, let's do this map. So, in order for this mapping to become a representation, what do you think this map should have a property? What do we want to maintain? What group? The group identities. And also what's the group come with, a operation, right? We want to maintain that operation as all sorts of map we defined yesterday. When we have a map, we must have a property that we preserve the multiplication. And as verse says that we need to preserve our identity. So, preserve multiplication to be our matrix multiplication, which said if I have an element G1, and then map to some matrix, have an element G2, map to some matrix, they multiply together, must be the matrix that G1 times G2 map to. So if it satisfies this, we'll call it a representation. And of course, we said that DE should be mapped onto identity. Okay. So there's a note about this. Let's take a note. So as I said, we just want to map group elements to matrices. It doesn't have to be distinct. Do not have to be distinct to become a representation. So I can totally choose the following choice. I choose to map all the G to identity. So I said, for all G, DG is identity matrix. That's certainly a representation. It has identity, and the identity matrix multiply each other with equals identity matrices. So this is a representation. Well, the problem is that looking at a bunch of identity matrices, we can't really learn much. So this is called the trivial representation. It exists always, but doesn't help us to understand the structure of groups. Since you can do this to every group, then how do we distinguish our groups? But it is a true representation. And then, of course, we love them to be distinct. We actually love to map different matrices to different group elements to different matrices. And if that happens, we'll call it a faithful. And when it doesn't happen, well, as English goes, you call it unfaithful. Okay, so that doesn't happen. And for example, we always have our trivial representation. That is not very faithful. Okay. So the next thing we want to understand is that we can have all sorts of choices of this map. And we want to define the equivalent class. So what do we mean by D? Some representation is equivalent to some other representations as D prime. Well, it's useful to know that, or else we just have tons of representation. So if we make some of them equivalent, then we can only need to study the one class. Well, so they are matrices. So remember how we learned about matrices. They are really linear operators acting on states, on vector space. So if we do some coordinate transformation of the states, some linear coordinate transformation of the states, then these matrices will also transform in the following way. So now we're going to introduce the idea of the equivalent is that if there exists invertible matrix S, which is basically the coordinate transformation, then we realize this representation is nothing but the similarity transformation of the first representation. So if two representations are related by a linear coordinate transformation, in other words, by a similarity transformation matrix S, then we call them equivalent. Because the physics doesn't change, we're just changing coordinate. Very good. Now we say, well, we're only really interested in the inequivalent representation. If you're equivalent, I'll study one of them, and all the rest I can just transform some coordinate together. Okay, so then we can define what you probably have heard a lot, what is called a reducible representation. So now we realize we can just play with our matrix S. Just find a matrix X and acting on this element in this following way and trying to find some easier representation to study the equivalent anyway. And a reducible representation is say that if we can find such matrix S such that after this transformation, what do we get? Is block diagonal. So of course, we require each of these guys still a square matrix. So let's say A1 is some square matrices with D1 times D1, etc., etc. And of course, we require all this dimension better add up to our M. And also we require Q is bigger than 1. Ooh, bigger. So we have at least 2 blocks to be called block diagonal. So this format of matrix everywhere is 0 is called block diagonal. And if we can put our representation in such a format, then we call it reducible. And then we can define what is the irreducible representation, also from now on referred as irrep, as you might have heard of about the particles we see in this world live in some irreps. And we'll actually see in the tutorial. Okay, so we define irreducible, well, it's IR in front of that word, so it means we can't find such as. We tried really hard, we exhausted all our searches. Now we can make them into block diagonal. Okay. So what we're going to do is given us a representation. We can always try hard to make them into block diagonal, which is just a direct sum of these irreps, which tells us the only thing we are interested in is irreducible, inequivalent representations. Okay, so we successfully put all our group elements into matrix form in the following way. And we convince ourselves the only thing that is interesting is the irreps. Okay, any questions so far? Okay, so let's move on to the structure of the group. So what do you mean by structure of a group? Well, actually, let's focus on our topic. Let's focus on the Lie group. So recall, Lie group satisfy all these group axioms, but on the other hand, it depends on some continuous parameter. This tilde just means it's a collection of phi1, phi2, phi-n. And as we have already tried really hard to demonstrate that we care about the dimension of the group, which is the number of real parameters. So from now on, we consider this Lie group is already depending on the real parameters. So this n is really our dimension of the group. And also known as the number of free real parameters. So you can totally define your matrix with some non-free, non-real parameters. But eventually, we're going to all get boiled down to a bunch of real parameters. So now it's just a very convenient choice. We're going to choose when everything is 0, we map to identity. It's just convenient. All else, when we do things in the future, we have to still move everything back to 0. We like 0. As we will soon see, in about 10 minutes, we'll see why we love this to be 0, and this gets mapped onto identity. Okay. So what do you mean by structure of a group then? Well, so what we know is that G, so I'll introduce some notation. So I'm going to use the upper index alpha, beta, gamma, they are just index. They are really labels. I can totally label them as apple, bananas, oranges. They are just a label, never summed over. It just keep track which parameter from which element. So I'm going to manipulate a bunch of these parameters, and I want to keep track which guy from which guy, because we're going to multiply two things together. So what we say is there's going to be a group element, G alpha, depend on phi tilde alpha, and multiply by another group element, depend on some other parameters, and they gave us some third parameter, depend on phi tilde gamma. So this is really group multiplication. We are given this by the group. And remember, these are just labels. I could totally do changing all this to be red color, green color, blue color. But we decided using these labels. All I can choose circles, triangles, square. What am I saying? They are labels. They are never summed over. We don't do anything. We just use them to tag the group member. Okay. Well, from this, so there is a structure of the Lie group. So if the multiplication of this two elements give us this element, so we believe this guy must be a function, tilde, f tilde, depends on the other two parameters. So if you give me two sets of real parameters, I should be able to find a function mapping these two sets of real parameter into a third set of real set parameter such that they satisfy the group multiplication. So this is what we meant by structure of a group. So really, our goal, our noble goal today, if it has tilde, it means has bunch. It's a set. So tilde always means it's a set. So if it has a downward indices, means 1. And the upper index is just a label. I just can't draw bananas and apples all the time. So I'm still using this Greek letter. I also want to use Chinese characters, because that is more, describe the vast, gigantic amount of elements we have in the Lie group. But anyway, our goal is to find this f tilde. We shall try to achieve this goal. Let's make some trivial, but enlightening observations. Why they are enlightening, we will soon see. But they are not hard to make. For example, I can make an observation and say, what if I take both the parameters to be 0? Well, let's do that. Let's go back to our group multiplication. That's identity times identity. It equals identity, which says our parameter is 0. Trivial observation, number 1. So let's try to do something slightly harder by only taking one of them to be 0, and the other just keep to be whatever it is. So let's do this in our group multiplication. It says identity times J beta. Well, by the definition of identity, this gave me J beta. But the J beta is described by these parameters. So f tilde equals to phi tilde beta. Is it clear? And I hope I can just convince you that if I take phi beta tilde to be 0, I'll just get a phi alpha tilde. So these are some trivial observations. So if you take one of them to be 0 or both to 0, we know exactly what it should look like. It comes from the group multiplication. This is basically the definition of identity. Question?
Are the coordinates of each group element unique?
So yes. When we talk about the Lie group, we'll make sure that we talk about the Lie group that all these parameters map to a unique group element. So that's how this is going to work, right? If we knew it's going to be mapped to J beta,
Then
we
we
say
know.
the parameter has to, it's a very good question. Yes, we need it to be unique.
So that's F tilde is well defined.
F tilde is well defined. Question.
And when you write 0, that really means that all the phi 1, phi 2, phi.
Very good.
Yeah.
Very good question. Let me make a tilde on the 0 says everybody is 0. No exception. Here. Good. Very good. So let's try to move on. Okay, it's very important. You are with me every minute today. Okay. So very good. But the first step is clear. There are 3 trivial observations of this F tilde. And of course, unfortunately, this is not what we truly want. We want the F tilde of the function of all positive phi's. How do we find F tilde?
I'm sorry, Carl.
Yep.
Can I interrupt again?
Yes.
So here we are like doing operations on the whole group as a whole.
So what do you mean? Which
So if we take G0 tilde, that means
J0 to E.
I mean G0 tilde, just
Yes.
G0 tilde. So
Yes.
that means we have a set of
Parameters.
parameters which are all 0.
They are all 0.
So and these are the parameters in the group.
These are the parameters. It's like, remember our our O3? It has theta 1, theta 2, theta 3. We say when all the rotation angles are 0, it means I'm not rotating. I'm just standing still. That's the identity. That's what we meant. Yes? Question?
That just brought up an interesting point. Yeah, because O3, like your angles are only uniquely defined from 0 to 2 pi.
Right.
So that means if you like, do we let our parameter only run from 0 to 2 pi, or do we just say we run the pi to 2 pi and then we just?
We can do some equivalent definitions, right? So we can always define 0 to 2 pi as the period. If you get some number which is 2 pi plus 2 pi, you map it back.
So our parameter space doesn't have to uniquely correspond to a group element. Then?
Well, it's the equivalent class of the parameters corresponding to a unique group element. So it needs to be unique, or else it can't go back.
Yep.
What I'm just worried about is that we are
Yes.
just making, when we are multiplying G alpha, phi tilde alpha, and G beta, phi tilde beta,
Yep.
we are basically multiplying
Two
two
group elements.
group elements, but
Right.
we have 2 sets there.
The group element itself depends on a set of parameters.
Oh.
But that is one group element, multiplied by one group element. Yes.
So basically, the indices on the G's
Right.
are just saying that the G's depend on the set of
Phi.
the parameters
Right.
phi alpha.
Right.
So basically, if we, for example, wrote G beta of phi alpha, that wouldn't make any sense.
It wouldn't make any sense.
Oh, okay, so
Right.
so
Like you are actually completely correct. Let me do this. Let me erase all the indexes
yeah.
of the G. So G is just a function of this value. But so it's for this 2 minutes. So but I could add here. I don't. Well, okay. I'm not that tall. Some expectation of myself doesn't work. Okay. So that makes more clear. G is just a function of my G. But when I refer G beta, it's really referring to this whole thing.
Yeah, sure.
Okay. Any other questions? So it's all clear now that what we first observations. Okay, now we want to find the F tilde. What have we said? There's, continuously many infinite number of group elements. So you can think of this is really a monstrous task. It almost feels like mission impossible. So we need to tame this monster. So practice, how do we tame this monster? Well, so now we can review the secret. Is that review the secret by using the mechanism, the machinery we just developed. First, we're going to only start a representation. Okay. So let's consider a f by m representation. So, well, remember, I'll just help us to remember, we only consider unitary representation. I know the other exist, but that's what I'm going to consider. So we're going to consider unitary representation that depends on G alpha. So remember, G alpha is just G as a function of this alpha 2 to alpha. So it's one element of the group mapped onto one m by m matrices. And I'm allowed to multiply by another such matrix, which should give me the other matrix. Some question?
So when you say it's a unitary representation, you mean you want to take a representation where those things unitary, where every element maps to unitary?
Oh, right. That's all I meant. What I meant is all these matrices are unitary matrices.
Yeah.
Because Wigner says that only two types are interesting, unitary and linear, or antilinear and antilinear. We're only interested in unitary. For now. Well, for the whole class. We'll consider U. That is that U dagger U equals 1 is what we say.
And UG alpha is one matrix which
Right,
depends on the parameters phi tilde alpha.
Very correct. That's the next one I'm going to write. Is that what we are really saying is U as a matrix defined on that set of parameters should give us. So look, this is just like a middle mind that we can draw. What we are really saying is now our group multiplication on a certain representation. I'm very bad with articles. Okay, so it's really a matrix depends on the parameters that the group element depend on. And another matrix depends on another set of parameters. Well, should equals to my matrix depend on f tilde, because f tilde is supposed to be the function of the other two set of parameters. And how is that helping us? Well, not yet, but remember, we are very, 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 very love identity. Identity is beloved to us. From the lecture 1, I'm trying to emphasize we want to live in the vicinity of identity. We want everything to be able to continuously going back to identity. And this is why. Because if we live close to identity, we can do the following thing. We're just going to, from now on, take them to be some epsilon, which is just some small parameter. And in that sense, U as a function of some set of parameter that I can expand. This is called the Taylor expansion. Since I'm living next to the identity, the first entry is the identity matrix. And then I can expand around these parameters I choose, and I'm going to call these matrices TAs. It's just a name. And this I is actually very interesting. It just makes, in the future, we get Hermitian operators, which are observables, which are nice. It's just a convention. You can totally choose without I, but then you're going to redefine your things to find your observable. It's just a convention. This is the imaginary number I. Okay. This is Taylor expansion of this matrix to the first order question.
That alpha you've got on the A and the TA as well, they are indices, am I correct?
Yeah, this is a very good question. A runs from 1 to n, which is the dimension of the group. We have n of this. So like this guy doesn't have tilde anymore, so this is one real parameter, say from 0 to 2 pi, or 0 minus infinity to infinity, depending on which group you want. And these indices do run. And what we know is that there are these n of these TAs that will generate the group hence acquire the name the generators. So our letter N now acquires new meaning. It's the dimension of the Lie group. It's the number of real free parameters. It's also the number of generators. They are all the same. They are all. Okay, so such a first order linear expansion must be valid. I can think about doing some derivatives. Okay. Very good. So as we might mention again, whenever you do a linear expansion, taking these TAs just be M by M matrices, you might be lose something. Because we do require these are unitary. If you just throw a bunch of TAs in, it's not a guarantee going to be unitary. We want our expansion at least to satisfy the condition that U dagger U is 1. So let's check that. Okay, so the following thing I'm going to do is basically copy that thing twice. You have to keep in mind that 1 is identity matrix and TAs are matrices. They have M by M. They are matrices. But I'm going to stop writing them. So your dagger is just E minus I. But these guys have real parameters. You know, that save us trouble. We only consider real parameters. But TA, of course, acquire the dagger. And now we can just copy the U matrix over here again. Well, it's just two different indices. But they are all summed. This one doesn't get dagger. Okay, so this is what we require. Let me write all my ones bold so that they know they are matrices. Okay, let's least expand this. We must be very good at this. Zeroth order. Well, we get a 1 equals 1. I'm happy. First order. So first order, we get this one multiplied by this guy. But it's identity matrix. So we get I epsilon B TB. And I have this guy's minus I epsilon A TA dagger. Well, the right side is identity. That doesn't have a linear term. 0. Okay. So now let me remind you. All these indices come in pairs. They are summed over. So they are considered to be dummy. It doesn't matter if I just call my B's. Ain't no. Yes,
I want to say you have to call your B's A's because otherwise you'd have different U's, right?
No, you're summing over there.
No, we're summing over.
Oh, summing over, right. Okay.
So remember there is this Einstein convention.
Yep.
So it doesn't matter. We're summing over all over all.
Yep.
So that right, let me emphasize. In that expansion, the indices are summed over.
Yep.
Okay. Or else we can't expand a arbitrary matrix in the vicinity of identity. So now this expansion guarantee we get everything around the identity. And after this change, but epsilon A is just some parameters as long as non-zero, which I can always choose that to happen. You get this very useful information. TH that equals TA dagger if we have a unitary matrix. So that tells us our generators are Hermitian. So TA, our generators are Hermitian. Okay, that's good. We know expansion, and we're going to use it. So remember our task is to figure out how this thing can work. I've already taken our phi's to be epsilon. I already said we can expand these guys in the following way. But then there's F tilde. where f tilde is a function of, let's say, epsilon tilde alpha. Remember, alpha is just a label. I can say that's a circle, that's a triangle, it doesn't matter. Those are just labels. It says I have one set of parameters, I have another set of parameters. Oh, in principle, we're just doing expansion, right? So, I know how to expand this. If I consider the ace component, we would have a zeroth order term, a linear order term in the first set of parameters, another linear order term in the second set of parameters, and then we're going to have, which is linear in both, which is in quadratic in both parameters, because apparently linear order is not going to tell us anything new. So we have to continue our journey. So let's expand. Then it could depend on quadratically from the same guy. So that's the completely exhausted sets I can think about f tilde. Any f tilde I can think about of two infinitesimal parameters must have such expansion. You're like, you must be kidding me. Yeah, we need to find all of them. All these things. Not really. Okay. Remember, we have enlightening observation. Ah. We know f tilde at 0, 0 is 0. That immediately tells us this guy doesn't exist. We know f tilde at 0, phi beta tilde equals 0, valid for all phi. Oh, sorry, phi beta tilde. So in particular, this guy needs to be valid if I take a epsilon beta tilde. Okay, so what does this tell us? This tells us this guy needs to be the chronic third type. That's how we can get this guy. And this also tells us this guy vanished. Because remember, when we draw these conclusions, we didn't assume they are infinitesimal. It holds for all orders. It means the second order of this expansion is 0, doesn't exist. There's no expansion. That thing holds always. We don't need to expand to know this. Remember, we made all this observation way back before we expand anything. Okay, so now you can convince yourself that if we put the other enlightening observation in, we find that this guy is also just a chronic third. And the e's also disappeared. Huh. That's nice, right? So this guy disappeared, this guy basically disappeared, that disappeared, this disappeared, this disappeared. We're left with this guy with kind of constraint, because it's coming from one of each set of parameters. Right? So what am I saying is, this monstrous expansion boils down to two terms that we know, and one term in second order we don't know. So I'm going to write this result over here. Okay, so very good. As we convince ourselves that linear order is not going to be good enough, we can either need to expand to the second order. We have the following interesting result. F tilde at the second order is completely determined by a set of numbers at this point has the name D with subscript BCA, and all these things round from 1 to n. Otherwise, the form is determined, the linear part is determined. So what we learned so far is F tilde as a function of e to the alpha, e to the beta at the eighth component is really the eighth component of alpha plus the eighth component of beta, and plus this D, C, B, C, A thing that we haven't earned any information on. Okay, so this is the expansion we're going to do with this F tutor. And this is pretty nice. Come on, we have like A, B, C, D, E, F. Now there's only D. All right, in order to do a second order expansion, in the sense that we have also to expand our U further. So before we only have expanded to linear order, that's apparently not enough because linear order tells us the generators are real. It doesn't tell us about F tutor. Okay. Well, we know how to expand it. First, it's I times epsilon A T A. Now we're just going to write more things like 1/2 epsilon A, epsilon B, some other matrix A, B. Right, that will be just a general expansion to the second order. The second order must depend on the quadratic order on the epsilons.
Should you read minus there?
It doesn't matter, really. You can put a minus sign. The plus sign, do the same derivation, it just disappears. But yeah, sure, we can put a minus. Well, let's stick with plus. And if I change the sign in the middle of my notes, I might get confused. But you can check. I checked. I also asked the same question. But it doesn't matter because I didn't say anything about the LAB. This is not, it's really this guy's double derivative, and if I have a minus sign, then there's a minus sign absorbing this. Okay, the only thing I want to mention at this point is that these guys are symmetric. Well, okay, we can choose to be symmetric because this part is symmetric. So the anti-symmetric part of this doesn't contribute anyway. So I'll just choose them to be symmetric. Okay, very good. Now we have expanded everything we want to the second order. Now we're just going to plug everything in this formula. This formula is pretty important, so let me rewrite it. At close to infinity, that the formula looks like a matrix depend on some infinitesimal parameter times another such matrices should give me a matrix depend on F tutor. All right. Any questions so far? Good. So before we start this long derivation, well, it's pretty long, I want to make a promise. This is going to be fruitful. Okay, it's going to worth our time. We're just going to compare the two second order. It's not that hard. We're going to do it together. All right, this guy, let me write. It's just very long. So left-hand side, it says one such matrix look like that times one such matrix look like this. And then now you see I have to label them. That's why there are these funny labels. But there's not much I do with the left side. I'm just copying things over. And then I'll add the labels a bit later. Okay, this is my alpha guy. Okay, and then this is my beta guy. To be not confused later, I'm just going to label them with some other dummy indices. Because with Einstein convention, they say a pair of indices with sum over. And if you have 3 indices, that would just be so super confusing. So that's I'm just changing the index. But they are dummy indices, so I can change it back later. We can do whatever we want with those indices. And this is really just copy 2 matrices over. That's our left-hand side. Not too bad. If you multiply them all out, there's only like 9 terms. Okay, the right-hand side, I'll use a new board. So remember remember what we're doing so far is something we probably do all the time. So we're doing linear expansions to some certain order. And if the first order didn't work, we'll just go for another order. It's nothing fancy. But hopefully, it'll be fruitful. Okay. So let's expand the right side. The right-hand side, first, it's a matrix. So I must be able to use that expansion. So I'll write it as 1 plus I, except now I have F A. Because my argument is F tilde now. Right? And TA plus 1/2 F A F B L A B. Okay. And then this is the long part. Because we actually know what FA is. FA is that expansion. Okay. So now, let's put our information of FA in. FA is the sum of this two small parameter plus this D things, who knows where it come from. Okay, so that's our F, and we need to multiply by this by T. That's just this term. One more term to go. 1/2. And then I'm just going to make 2 copies of this. Okay. So this guy has index A. Let me choose some different size indices so that they will all summed over a pair, not like a bunch of them. Okay, so that's 1 copy. And then here's another copy. Okay, right? There's not much. It's not fancy. I'm just say I replace F by that expansion, replace this 2F by that expansion. And you keep track of the indices, make sure you all choose different indices to sum over. This is where we are. Okay, now we only need to compare to second order. That's actually really nice. Because you realize the F itself is in the first order already. So we can immediately say this guy's, we don't care about these guys. They look horrible, but we don't care about you. You guys at most gave me third order, which is already beyond the scope. Oh, so slightly better. Okay, let's do the zeros order. Well, hopefully the result doesn't surprise you. It should give us 1 equals 1. Very, very enlightening result. Okay, first order. Okay, so it's that guy equals that guy. So the first order would be the identity times, that's why they have hockey sticks. Okay, first order is this guy identity times this guy and that guy times that guy, right? Let me just copy it over. It gives me I epsilon A alpha TA plus epsilon C B TC. Oh, there's a missing I. Ooh, that's very bad. I'm back. Oh. Some typos are always there. Okay. Okay, and there's an I. And then let's look at the right-hand side. The right-hand side we have, well, I epsilon A alpha times TA. I epsilon A beta times TA. Oh, also 2 terms. That's promising. A alpha TA plus I epsilon A beta here. Okay, the only thing I need to do is rename these C's to be A's. Very cool. Good. That's called a sanity check. It works in the first order. All right, let's see. But the insight will be provided by the second order. So second order is basically that one times that guy. The one on the first line times that second order guy. That is second order guy times that one. And the cross term from the linear order. So 3 terms. Okay. So left hand side give us, there is 1/2 epsilon A alpha, epsilon A beta, L A beta. And there is 1/2 epsilon CD. Wait, nope, this is all alpha. And this is all beta. And then there is the cross term. The cross term, 2 i's give me minus sign. And then we have epsilon A alpha, epsilon C beta, and TA, TC. Okay. Now we just have to look at what is on the other side. So right-hand side. There are some terms comes in. Sorry. For the first bracket, we have I times D, this bunch of things times TA. So that's I, D, DCA, epsilon B, epsilon C, alpha, beta, TA. And then it has a bunch of terms. But remember, we already threw away those 2 terms. So it's 2 multiplied by 2. So there are 4 terms here. Okay. So that is 1/2 epsilon A alpha epsilon B LAB. And then 1/2 epsilon A alpha epsilon B beta LAB. And then there is epsilon A B A beta epsilon B alpha LAB. And there's the last term, 1/2 epsilon A beta epsilon B beta LAB. Okay, the only thing we need to do is to set them to be equal. Whew. Okay, let's do some insightful observation. Let's look at this guy. Ooh, that's a B. Okay, let's look at this guy. This guy showed up again here. Cool, they canceled out. Then let's look at this guy. This guy showed up with 2 beta. That guy also canceled out. That's nice. And if we look at these 2 guys, they're the same guy, that they are symmetric, right? So these guys merge. That's not bad. Totally not bad at all. We're left with 1 term on the left, 2 terms on the right. Yay. Let's collect this result and say, the best part is the things we interest called this D things, which tells us what the F tilde would look like, is there. And I'm going to write those two terms in one term since they are the same. And so I can drop the 1/2 because I have 2 copies of U. Okay, so this is what we learned from comparing to the second order. Okay, so let's do some.
Sorry.
Wait,
Isn't
there?
missing a TATC in the
Yes,
side?
you are very, very correct. There must be something get lost. Thank you. Or else the indices doesn't get a sum. Very good. So now, well, remember this epsilons, the goal of expanding them is try to drop them later because we don't want any result depending on which particular epsilon we choose. So let's just rename, the only thing we're doing now is renaming my indexes. For example, in this term, I'm renaming C into B. And the index, I have to do something slightly more convoluted. I'm going to rename B into A, C into B, A into C. So I get A, B, C. Right? I'm just renaming. The idea is after as this renaming, I accomplish the first goal, is get rid of all the epsilons. They should be work for all epsilons, so then they should work without them as well. It's called cancellation law in multiplication. Okay, very good. So what are we left with? Is minus TA, TB equals I, D, ABC, TC plus LAB. Okay, but come on. We already have n matrices, our generators, they are observables, they are so nice. I don't want another n square of this, guys. What are they doing here? Let's try to cancel it by switching the index. We switch index A and B. Ooh. Because they are symmetric. Now I can just subtract them. And this not very useful else will just disappear. And hence, at the beginning when I expand, I was a little bit sloppy about that minus sign because in the end, this term doesn't matter. We're going to get rid of it. All right. So what do we get out of here? Is something some of you might have already seen. Let me just write down what do we get by subtracting those two equations. We're going to use 2 subtract 1. To match some conventional definitions. So 2 subtract 1 will give us positive TA, TB. Subtract TB, TA equals I. D, B, A, C, subtract D, A, B, C, T, C. And all the L's are gone. Cool. Now, we're just going to call the first 2 indices anti-symmetric part of D, giving them a new name that you might have heard. It's called FABC. And if we look at on the left, this is what we call a commutator. So we say commutator of TA of TB equals I FABC TC. And this is the main result of today. Question?
Where did we show that LAB equals LBA?
Oh, so when we look at the expansion, you can just look at that one. If I switch indices A and B, I mean it's A, the first FA that hockey stick. If we just look at this, so it's somewhere So, but if you look at this one, if the FA times FB, these are just two numbers. So this part is symmetric. So I can just choose this to be symmetric because the anti-symmetric part doesn't matter. So they are not, well, you can choose a not a symmetrical one, but you can choose them to symmetric because that doesn't affect our expansion.
Okay, sure.
Okay. So, are you with me? Good. Because now we're going to do the third order. Now, why do we do that? Come on. Now is the time to harvest the fruit. This is our fruit. Georgia will show this is good enough. If we just have this commutator relationship, that thing we try to show that will hold to all orders. Well, the argument is like this. So remember, when you do this to the finite, go back to the finite, not the infinitesimal around the identity, what you do is you do an exponential thing. And there is a formula tell you e to the a. So there is an enlightening formula says if I'm multiplying. So I'll try to hand wave why this is good enough. So recall, so now I'm happy because I say, I'm just going to expand to this order because it's good enough. And what we're going to do is that, suppose now I'm interested in that phi tilde, which is in general not infinitesimal. What we're going to do is just going to chop this into a big number of pieces such that each piece is infinitesimal, and then we're going to do n times. And this thing is what we define to the exponential. So this tells us that we can do finite things as long as we understand the vicinity of the identity. And there is this interesting formula that says e to the a times e to the b is something a plus b plus or minus, I forgot, 1/2 ab plus a bunch of other terms. But the insightful part is all this many, many terms has only commutators in it. So that tells us this is good enough. That's all we need. And this thing is called the Lie algebra of a Lie group. So algebra is just there's a set we define a binary operation that goes back to some linear combination of that. So since it comes from a Lie group, it's called the Lie algebra. So this is, I consider, very fruitful. And first thing, we should look at our struct constants a little bit more carefully. Because since they're so important, they're called structure constants because they determine the structure of the group. So if they have some nice properties, we shall try to discover them. Well, the first thing shouldn't be hard. This is anti-symmetric in first two indices, in A and B, because it's defined in the commutator. Let's try to be more insightful by taking this definition and let's take the dagger of it. Well, we're talking about unitary matrices, so we can always take the dagger of something. Okay. We're taking the dagger of it, I become minus I. FABC become the conflict conjugate, and this guy become itself because it's a Hermitian. Okay, let's try to see what this guy is. This is TA, TB, subtract TB, TA, dagger. And according to our dagger rule, it becomes TB, dagger, TA, dagger, subtract TA, dagger, TB, dagger. But those staggers are not here. They are Hermitian. So this is really TB, TA's commutator. Right? Well, we know what's TB, TA's commutator. It's just minus that guy. So this guy equals minus A, F, ABC, TC. This is very insightful. We realize our structure constant are real. I like real numbers. That's like so much fewer numbers to think about. So they are real. Okay. Then let's make further observations. So this is the operation. This is the operation in a algebra. We can certainly ask, is this commutative? Well, it's not, because it's defined by a commutator. It's by definition anti-commutative. But we can then ask the question, is it associative? Because by our definition, it's a multiplication after all. So what do we want to ask? Is this guy, yes, is this guy equal to that guy? Well, if you have been playing around with matrices and commutators for a long time, the answer is no. Because for any matrices, generators or not, for any matrix, let's just call it X, we have the following nice relationship. If we just, okay, let me just cycle the indices later. So that's B, C, A, C, A, B. Well, the secret is really useful. Okay. So for any matrices with commutators, you can always show this is true, which is known as the Jacobi identity. This is not hard at all. They are commutators. Just expand them all. You have 12 terms. And you get 6 pairs. They all cancel. Okay. And then, well, since they hold for any matrices, we can certainly take them to be our generators. And then we observe the following interesting thing. Because we know the generators of the commutator of the generators actually give you structure constants combination with some other generators. Hence, we have this Jacobi identity of the structure constant. So if we find a Lie algebra and the structure constant always satisfy the Jacobi identity, which is only just coming from the commutator relationship. This is not hard to show. Let's just take one term. Let's take this guy. By definition of structure constant, this is F, F, A, B, D, T, D. Then F are just a bunch of numbers. Let me pull it out of the commutator. And this is another commutator, which of course gives us some other constant, which is I, F, D, C, E, T, E. Right? So what do? Is we do it for every single term. Then you get 3 terms. And then you switching indices around, you get this. Okay. So this is very nice. Because sometimes, well, you know, if I already got the Lie algebra and then you say the structure constants have the following property, it's nice, but it's not as useful as if this is a Jacobi condition. So Jacobi condition says, as long as I find this bunch of numbers, they satisfy Jacobi condition, then we can form a Lie algebra out of it. So structural constant is really everything we want. Hence, we spend all the time on it. Okay, so this is the time I say, hooray, because, hooray. This is the triumphal moment. Yes, question?
So can I check? The TAs and TB, like the TAs are the generators of
Right.
the algebra,
Yes.
and the FABCs are just the structure constants that just determine the commutation rate.
Yes. Exactly. Then we'll learn something more about it next class. But this is the time we say, hooray! Because I have a recipe. It says, give me a Lie group when the expanded, find the generators, find the commutator relationship, commutators, then I get a Lie algebra. Then I can just focus on my Lie algebra, find everything I want to know, and then completely forget about the Lie group, because we're just going to exponentially didn't get it back. Okay. So, in the next 5 minutes, I'm just going to do something with the complementary group, rate group, which we're going to spend the whole afternoon on it. Hopefully not a whole afternoon. Okay, so what do? Is let's grab this pretty complicated group. And we want to expand it. So remember compound array group we talked a little bit last time. It's made with some lambda and A. Lambda is a Lorentz matrix and A is just a 4 vector. And this lambda satisfies the condition that A preserves the metric. So on the other hand, we know that E to mu rho sigma gives E rho sigma. So this is just with this index is restored. So what are we going to do? Is we're going to expand lambda around delta, which is a 4x4 identity matrix, and we'll call there's some small parameters called W. And then, as always, we need to do a sanity check. We have to check our expansion actually is going to give me a Lorentz transformation. It could give me anything. So let's do that. So we have, okay, let's do that. Just plug this in, plug that in, expand to the first order. So we'll do that in the tutorial. But the conclusion is omega is antisymmetric. It involves a bunch of raising, lowering indexes with etas and delta, but there's nothing tricky there. Okay, this is very good. Question?
Should be a minus where?
Correct, or else it's symmetric. Very good, thank you. What I meant is that. Okay, this is very good. Because in principle, they are 4x4 matrices. If it's antisymmetric, we're left with 6. So the same 4 times 3 divided 2 formula that I have told you. This is good. It indeed have 10 parameters. So, of course, the next thing to do is to expand it. So for any element, can you see this one? Mm-hmm. Okay. We're going to expand it around this small parameter W, small parameter epsilon. They are just the parameters we talked about before. So again, it's equals identity. And there is the following convention has been followed for a very nice reason. Because if we follow this convention to choose to combine them together with such i's and half and stuff, then these are very physical. because Poincare group describes the symmetry of Minkowski space. So as you probably imagine, P0 is our Hamiltonian. P1, P2, P3 is the momentum. And then we have J, 2, 3, J1, 3, 1, J1, 2 is the angular momentum we talked about extensively in quantum mechanics. Then we're left with a boost. So that's our 10 generators. They are all m by m matrices, but they are just grouped such nicely into our observables. And of course, as I told you, that we want to find the structure constant, the commutator relationship between all these things. That's what we're going to do in our tutorial. The result is here. So this is called a once of a lifetime calculation. So if you have done this, just move on. This is the result. Okay, so there's something very insightful. We can just look at the result. Is the momentum commute with each other. The best part is momentum commutated with other stuff come back to momentum. As you probably realize, this is something we define as invariant.
The translations.
Oh yes, the translation. The translational group is the invariant subgroup. And that's why we call this a semi-direct product, not a direct product. Because this part is invariant, but the J is not. And the one last remark is you're going to show in the tutorial P squared, defined by P nu, contracted by eta mu nu. This guy commutes with everybody. That's very nice. Means if we do a Poincare transformation, which means moving observer in any way you want in this 4 dimensions, this thing's not going to change. That's why it's called minus m squared. And this is what we mean by mass of a particle. It's the thing that it commutes with everybody. Okay, so that's the end of the class. And tomorrow, we're going to study everything about SU2.